Howdy, today on Flipping Science we're looking at different metal production methods. So you need to be able to explain why the production of aluminium requires a molten non-aqueous electrolyte, explain why zinc and iron can be obtained using carbon, whereas you can't do that with aluminium, predict the likely method of reduction of a metal compound given its position in the activity series, explain why reduction using electrolysis is preferable to electrolyzing a melt. So we're going to start by looking at aluminium production in a little bit of detail. You don't need to know many of these details, but it's interesting to go through anyway. So aluminium is quite a reactive metal, and it's so reactive that you can't reduce it using carbon as a reducing agent. Carbon you can use for things like zinc and iron, but it doesn't really work with aluminium because the carbon isn't strong enough as a reducing agent to reduce the aluminium ions. So instead they use a melt, and they use a molten salt. So the ore is first purified using what's known as the Bayer process, and then from that the aluminium oxide produced is electrolyzed with cryolite, and that's how you produce your aluminium. So we'll just briefly go through this process. So in the Bayer process, bauxite, which is the ore for aluminium, it's impure aluminium oxide. It's mixed with hot and concentrated sodium hydroxide under high pressure, and that produces sodium tetrahydroxide aluminate over here. The sodium tetrahydroxide aluminate is then cooled, and some previously produced pure aluminium hydroxide is thrown in, and that produces even more aluminium hydroxide. So it's the seed for the crystals of aluminium hydroxide to form around. From there, the aluminium hydroxide is heated and aluminium oxide is being produced. The aluminium oxide is then electrolyzed with cryolite. Cryolite reduces the temperature required to melt the aluminium oxide, so that's why it's used. The aluminium oxide cryolite mix is then put into the electrolysis cell, which looks like this. You have a carbon lining. That's the cathode, and then you have the anode, which is dipping in. Now I've labelled the metal lining as the cathode. It's not really. The aluminium in there that collects at the bottom acts as the cathode. So the electrolysis occurs. You get the aluminium ions being reduced to aluminium metal. That sinks down the bottom, and then that's tapped off. This requires an awful lot of electricity for this step. So oftentimes aluminium production is linked up with a cheap source of electricity, like coal, for example, or hydroelectricity if you can. So these are the reactions that are occurring in the electrolysis cell. So aluminium ions are being reduced to aluminium. That's the liquid aluminium that forms at the bottom of the electrolysis cell. Oxygen is initially produced at the anode, but then at the temperature that we're talking about, which is 1,000 degrees or so, the carbon anodes, they burn. So we're getting oxygen, and that's reacting with the carbon anodes to produce carbon dioxide and carbon monoxide. The mix of products you get there depends on the temperature. Because the anodes are essentially burning away, they're one of the big costs in producing aluminium. You have to replace them fairly frequently. So as we saw with aluminium there, it's quite a reactive metal, and that means it's got a very difficult reduction process for the reducing the metal ion to the metal. Metals that are less reactive than aluminium, you can use a reducing agent like carbon rather than doing electrolysis. So if we look at, say, zinc and iron, you can reduce their ions using carbon and carbon monoxide rather than having to electrolyze a salt. You can electrolyze a salt solution for metals up to zinc. So copper, for example, they use a copper sulfate solution that's electrolyzed to produce copper. So for these ones in here, you can use a salt that's in solution and reduce the metal ion from the salt solution. Above zinc, you need to use a melt, which means you have to produce a salt and then melt that salt at high temperatures and then electrolyze that. The reason why you have to do that is if you used water in the mix, as you do with the ones in here that use an aqueous salt solution of, the water will be reduced in preference to the metal that you're trying to reduce. There's a video that talks about that, and I'll link to that to the bottom down here. So here's a nice diagram that sums up the reduction processes for metals. So if we look at very active metals, they use a molten salt, so molten chloride or a molten oxide. For metals between zinc and lead, they can use the carbon or carbon monoxide to reduce it. For things like copper and some of these in here, you can also use a salt solution. You can reduce the metal ion from a salt solution. And then down here we've got silver and gold. They're found natively. They don't react with anything in the environment, so you don't have to worry about doing a reduction process at all. In terms of environmental effects, the reduction part of the process requires an awful lot of energy, and so it's the most expensive part of the metal production process. So if you use a blast furnace, so down here we have a blast furnace that's used for things like iron, you need to heat that up to high temperatures, and you need to provide things like gas or electricity to produce the really high temperatures there, and that can be quite expensive for the manufacturer. If you need to electrolyze a melt, more than 50% of the energy that you need is just used to keep the melt at the temperature. So for aluminium, we saw it needed to be at around about 1000 to 1200 degrees Celsius, the aluminium oxide cryolite mix. Just keeping it at that temperature requires half the energy in the whole production process. So we talked about a blast furnace. This is a blast furnace, and that's how you can produce very low quality iron. So at the top of the blast furnace you insert your iron oxide, coke, which is carbon, and limestone. That gets put in the blast furnace, which is at quite high temperatures. As it passes through the blast furnace, the coke produces carbon monoxide and carbon dioxide, and they're the reducing agent for the iron. So here's the equation over here. So iron oxide plus carbon monoxide goes to iron plus carbon dioxide. So the iron produced trickles down the sides of the blast furnace and collects down the bottom. You get a layer of slag being produced. That's your silicates, that are your waste products. And you tap off the iron down the bottom here. So again, keeping this blast furnace nice and hot, that's where the energy cost is in this process. So one of the things you need to talk about is using a solution versus the blast furnace or a melt. If you can, you use an aqueous solution, because an aqueous solution is very cost effective. The solution that you have, and this is for copper production down here, the solution that you have there, it's only kept at 40 to 60 degrees Celsius, so that doesn't require a lot of energy to do. Whereas if you need to use a melt, you need to heat up the salt to its really high temperature before the ions will separate and it will melt, and that requires an awful lot of energy. In the blast furnace as well, you need to provide a lot of energy to heat up the blast furnace so that it's effective at turning the carbon into carbon monoxide in order to so that it can reduce the metal ions. So if you can, use an aqueous solution. So let's have a look at some questions. It says, first one says, identify a suitable electrolyte for the production of sodium metal. Sodium, if we look at a metal activity series over here, and I stole this from one of the exams, sodium is quite high in the activity series. Because it's quite high, you won't be able to use a sodium solution, so you can't use sodium chloride solution to do this. So you're going to need a salt, so a molten salt. So molten sodium chloride would be a good electrolyte for the production of sodium, for example. Second question here says, copper can be used to make catalysts necessary for the production of methanol. Predict the likely method of reduction used to convert copper mineral into copper. If you look at our activity series, again we can see copper is right down the bottom of these metals listed. So that means we could use something like carbon or carbon monoxide as a reducing agent. In reality, what is used is a copper solution. Electrolysis for copper sulfate solution is used in industry to produce copper. So that's a likely method because it is the method that's used. Another part here says copper can be produced by heating its oxide with carbon. Explain why a similar method cannot be used to produce aluminium. So again, if we have a look at our activity series, we can see copper's down the bottom and aluminium is in the middle here. So carbon isn't a strong enough oxidizing agent to reduce aluminium ions. So that's the simple answer there. Because copper is less active, it's more easily reduced. So we can use carbon as its reducing agent, whereas aluminium is more reactive, which means it's more difficult to reduce. So we need to use a stronger reducing agent than carbon or carbon monoxide. Part 2 says, state one reason why the manufacturer uses zinc sulfate solution rather than molten zinc oxide as the electrolyte for electrolysis. By using zinc sulfate solution, you don't need as much energy. If you used a zinc oxide melt, you would have to heat up the zinc oxide salt to a ridiculously high temperature before it's melted, and that would require a lot of energy and therefore cost to the manufacturer. By using a zinc sulfate solution, you don't need as much energy because it's a solution. So the zinc and sulfate ions are there present. You don't need to heat it up to break it up. So it uses less energy, which is cheaper for the manufacturer. The next question says, titanium dioxide is used to prepare pure titanium for medical uses. Sequence of reactions is shown below. First part says, balance the equation for reaction 1. So we've got one titanium, that's okay, 2 oxygens and 1 oxygen on this side, so I'm going to need to double that. which means I'm going to need to double my number of carbons, and I've got 4 chlorines on this side but only 2 on this side, so I'm going to need to double that one as well. Second question says, state the function of carbon in reaction 1. Carbon 1 is a reducing agent. If we have a look, carbon here, if we were calculating its oxidation number, it would be 0, and if we look over here, the oxidation number would be +4. So it's got an increase in oxidation number, which means it's oxidized, and therefore it's a reducing agent. It's causing the reduction. Third part of the question says, explain why copper cannot replace magnesium in reaction 2. So why can't we put copper in here instead of magnesium? The answer is, if we have a look over here at our activity series, magnesium is much more reactive than copper. So here we're using magnesium as our reducing agent, so we need a fairly active metal there to be oxidized. If we try to substitute in copper here, copper isn't as reactive, it's not as easily oxidized, so it won't be able to reduce the titanium ions, which is what we want to have happen in this process. So copper is not a strong enough reducing agent for the titanium ions in titanium chloride. So today on Flipping Science, we looked at different methods of producing metals based on their activity. That's it for Flipping Science today. See ya.